2 and 3. So we are ready to talk about some of the different ways that we may go about collecting data. Okay, statistics is all about getting data, analyzing your data, and drawing some kind of conclusion from that. So we have to know how we might go out and get our data to start with. So I'm actually going to begin with an example here. So in your example packet, example 1 for today. All right, so this is one of those very wordy examples that I just took out of your book. So we have some researchers that want to investigate cancer risk among Danish cell phone users who were followed for up to 21 years. So to do so, they kept track of 420,095 people whose first cell phone was between 1982 and 1995. Then, in 2002, they recorded the number of people who had a brain tumor and compared that rate of brain tumors in that group to the rate in the general population. So they found no significant difference in the rate of brain tumors between the two groups, and they concluded that cell phone did not increase your risk of a brain tumor. All right, so without me telling you the difference between an observational study and a designed experiment, which one do you think this would be? Why? Okay, did they do anything to the people they put in their study? No. What did they do? They watched them. They said, okay, you have a cell phone, you're going to be a part of this, we'll check back in 20 years and see what happens. So they didn't actually do anything, they just observed. Okay, so let's look at this one. So these researchers went to examine if chronic exposure to radio frequency radiation at 2 different cell phone signals, so analog and digital, caused brain tumors in rats. So the rats in group 1 were exposed to the analog frequency, the rats in group 2 were exposed to digital frequency. Then they had a third group that served as their control group that had no radiation at all. So they did this 4 hours a day, 5 days a week for 2 years, and they kept everything else the same, except the amount of radiation they were exposed to. So after 505 days, they reported we found no statistically significant increase in any tumor type, including brain, liver, lung, or kidney compared to the control group. So is this an observational study or designed experiment?
Designed experiment.
Why?
Because they have them in a controlled environment and then did stuff.
Right. They broke them into groups and they did something to each of the groups. They didn't just sit and watch them. They exposed them to radiation and then measured after the fact. Do you guys see the difference between the two? Okay. Which one do you think would probably give you better data? An observational study or a designed experiment? Designed experiment. Why?
Because then you have like everything set of like what's going to happen.
They know everybody's getting the same amount of radiation. They kept everything else the same. So their diet was the same. Their exercise was the same. All the other things in their environment they were exposed to were the same. You know, in my observational study, if we had found an increased risk in cancer, did that really mean that the cell phone caused the risk? Not necessarily. It could have been the diet or the exercise or where these people live. There's so many other variables. So a designed experiment definitely gives you better data. Why would we even use observational studies then? It's easier, cheaper. You know, they just had to check back with them in 20 years and see what happened. Would it be ethical to take 420,000 people and say, okay, Eli, I want you to talk on your phone for 12 hours a day. I want to see what happens to you. Jaslyn, no phone for you. We want to see what happens to you. Can I do that with people? No. So a lot of times it's not ethical to actually subject people to some of the treatments. So they just have to observe and do their best with that. In each of these, what our goal was to determine how the amount of an explanatory variable, if we vary our explanatory variable, how it affects the response. So the explanatory variable, that's the thing we are messing with. And what happens from that is our response. So I think I have this a little bit out of order on your packet. I apologize. So on your definitions packet, I've kind of given you examples of observational study and experiment. I'll give you those definitions here in a second. But if you jump underneath that, the variables we study. So an explanatory variable, that is the thing we are changing. Okay, what is that in these examples? What was our explanatory variable? Radiation or cell phone usage, it was all linked to that, so either one. So the response is the outcome we are measuring. So we manipulate the explanatory to see what happens to the response. In this case, what was the response variable we were looking at? The effect of that radiation. Basically, did they get cancer or not? The cancer levels, we looked at several different types. Okay, so let's do our definitions for the observational study and design experiment. So observational study, you can put the definition I wrote here, we can also kind of summarize this. It says it measures the value of the response variable without attempting to influence. So observational study, you observe, you don't interfere. Okay, we just sit back and watch what happens. We're not actually controlling any aspect of it. In the design experiment, that's when the researcher is manipulating that explanatory variable. They're determining what type of radiation and how much radiation they're getting, and then use the response. A lot of times we're going to have multiple groups because we want to compare. What if you get this versus if you don't? One of my goals in this class is just to make you more aware. There are tons of statistics out there that are used all the time. If you watch the news, you see it all the time. 75% of people agree with this. 3% of the people will get this disease. They throw those things out there all the time. But you have to be very careful about knowing what you can and cannot believe in some of these things. So let's take a look at this example. So our researchers want to determine the long-term benefits of the influenza vaccine on seniors aged 65 and older. So they look at records of over 36,000 seniors over the course of 10 years. They were divided into two groups. Group 1 were those that got their flu shot, and Group 2 did not. So after observing them for 10 years, it was determined that if they got their flu shot, they were 27% less likely to be hospitalized for pneumonia or influenza, and 48% less likely to die from those things. Okay, so sounds pretty good. Does that mean everybody should get their flu shot? Not necessarily. Why?
Because it's not close to 100%.
Okay.
It's not guaranteed.
So, 27% less likely, that's definitely not super high. We haven't talked yet about, what is significant and what's not. So maybe that percentage isn't high enough to be convincing to you. What else?
Only 48% less likely to die.
Okay, only 48% less likely to die from it. So definitely not a guarantee.
They started observing them from 65 and then 10 years, so that's 75. That's near the life expectancy of average American anyways. They could have just died of natural causes.
Okay. Did this look at their health before they started this? No. Okay, so what we know is out of the group that got their flu shot, they were 48% less likely to die from the flu, which sounds good, but who gets their flu shot? Children. People that are probably going to the doctor, right? If you go to the doctor and they say, hey, it's flu season, you want to get your flu shot. What about those people that never go to the doctor? Is anybody telling them to go get their flu shot? So is it possible that out of this group, they were less likely to die from it because they were already going to the doctor on a regular basis? And so just by going to the doctor, they were more on top of their health and doing better? Sure, we don't know. Is it possible that the ones that got their flu shot were more health conscious and exercised more and ate better? So do we know if the being less likely to die is because they got the flu shot, or is it because they had a better lifestyle? Anyway, so there's a difference between saying there's a relationship and saying one thing caused the other. I don't know that the flu vaccine caused them to live. I just know that there was some kind of relationship there. So this takes us into some different terms, some things to keep in mind. Confounding. It occurs when the effects of two or more explanatory variables are not separated. Okay, so I could be looking at if they got their flu shot and if they go to the doctor. There is really no way to separate those two things. I didn't separate it out. So I don't know what was caused by getting that vaccine and what was caused just by the fact that you go to the doctor on a regular basis. I can't separate those effects, so there's confounding going on. So you don't really have to write down this little blurb. I was just kind of explaining that you don't know which piece is causing it then. There can be what's called a lurking variable. So something we didn't even think about that maybe has an impact on the study. Maybe those people that got flu shots did it because they had grandchildren they were going to be around and they didn't want to get their grandchildren sick. And maybe those having grandchildren that they were active and participating with actually had an impact on their lifespan. Okay, we didn't even consider that. That having grandchildren was a lurking variable, something that maybe had an effect, but we didn't even think about. Okay, so those are two issues that might result when we have an experiment. Two things that we need to keep in mind. We're almost done with all the writing today. I know writing these definitions is not fun. We're getting there. We just have like 3 more today. We're going to kind of start today, but look at it more tomorrow. How to create a sample. So I'm going to give you the first few terms that come up with that today, and then we'll pick up there tomorrow. So when I'm trying to get a sample to study, it's a lot of times useful to have a census. A census, just like when we have a census in the United States, what do? They give you paper, and what's their goal? Right, they want to count every person, right? So a census is a list of every person that has a characteristic we're interested in. So if we are studying the effects of concussion in high school sports, then what would my census be? The list of everybody I'm concerned with. Yeah, people involved in those high school sports that get a concussion, right? So I'd be looking at high school students that have had a concussion. That's my list of everybody. And then I'd pick my sample out of that. So a census is just a list of everyone in the population that has the characteristic we're interested in. Did everybody get that one written down? Last two definitions for today. So when we get into our sampling methods, we're going to look at random sampling, a list of, or a way to randomly select people to be in my sample. If I want to see if high schools or students in our school were excited after our assembly on Monday, then a random sample, the easiest option, would be just to put everybody's name in a cup and start drawing them out, right? When they were picking people to do the games on Monday, they spun the wheel. They got a random sample. They randomly selected people. Okay, so there's not a set method, it's just random who gets selected. There are several different ways of making that random sample, which is really what we're focusing on tomorrow. The first and the only one I'm touching on today, so if you look at that first box, is the simple random sample. And so basically in a simple random sample, every sample size is equally likely. Or another way to state that, each person has the same chance of being selected. When they put everybody's name on the wheel and spun for a prize, did everybody have the same chance of being selected? Yes. So that was simple random sampling. Everybody is equally likely. You have no advantage there. So we're going to do a couple examples and then we are done for today. So if you go to your example page, you have examples 4 and 5 that we're going to look at. So suppose a study group consists of 5 students. 2 students must go to the board to demonstrate a homework problem. List all possible samples of size 2 without replacement. Okay, when I say without replacement, that means can you go to the board with yourself? No, so once you're drawn out, you can't be selected again. Okay, it's not going to be Carly and Carly coming to the board. It'll be Carly and someone else. So, what's every possible group?
Bob and Patricia.
I'm going to abbreviate. Bob and Patricia, or we could have Bob and Mike, or we could have Bob and Jan, or Bob and Maria. Is that every group where Bob could get selected?
Yes.
Okay. Then without Bob, we could have Patricia and Mike, or Patricia and Jan, or Patricia and Maria. Or we could have Mike and Jan, or Mike and Maria. Or we could have Jan and Maria. You're going to have a homework question kind of like this. I think I intentionally made sure all the names started with a different letter so you could easily write down your groups. So you don't have to write them out full. Does everybody understand how we got those groups? Okay. So how likely is it that Bob and Jan have to come to the board? How many times did Bob and Jan show up on our list?
10%.
We had one time out of how many total? So it's a 1 in 10 chance, or 10% chance that they come to the board. All right. Is that one okay? So I want to lastly talk about how you could get a simple random sample. So there are a few different options. One of the most common ways is, it's not that bad just to list them out here, but if I had 100 students, do you want to list every possible combination? No, that would take forever. So there are random number tables. I know I told you you didn't have to bring your books today. So there's like an actual random number table in your book that you would just start, at the top and go through, and it has a list of random numbers that have already been generated for you. More often, we are just going to use our graphing calculators to get a random number. So if you would, go ahead and grab a calculator for me. In theory, you would like to say you could just make up a list of random numbers, but what comes to mind for you is really not truly random. We all have tendencies to select certain numbers over other numbers. So this is more truly random. The calculator actually has an algorithm built in to create a random number. So what you need to do first is pick any number you want. Is it dead? Okay, so you have to pick what's called a seed. So you start with a number. So I'm going to select 4. You can do 4, you can do something different. Then we need to store it. So above your on button there is an STO, that means store. Okay, and then we are going to go math. So you pick a number, store, math. We are going to be doing probability. So you go over to probability, and we want number 1, rand. So everybody get here. Number, store, math, over to probability, random. And you just hit enter. And it's just going to spit back the number you gave. Okay, this is like a starting point. If I started looking at a random number table, it's basically which column am I going to start in? You just pick one. Now we want to generate a random number. Okay, so now we're going to go into math, probability, and we want number 5, random integer. Okay, I think my calculators, I think it comes up a little bit different, doesn't it? Mm-hmm. Okay, so on my calculators, it just says random integer parentheses. So you have to tell it between what 2 numbers. So let's say we want to go between 1 and 100. So you would type in a 1, and then you need a comma. You guys see the comma by your parenthesis? Huh? Like I said, these calculators, it looks different than what's up there. So that's what I'm saying. You would type in 1, and then you type your comma. This is an updated version, and I can't go back to the old. So yours comes up. So 1, 100. that parenthesis and hit enter. And it gives you back a number. So this one gave me 99.
Wait, so just for the number, like the end, because mine's like yours.
Okay, I'll explain what that means in just a second. So just go ahead and do one for now. So sometimes I may need to select multiple people. So let's say I have 100 students and I need to get 5 of them for my sample. So I can give them each a number, 1 through 100. This tells me my first person is whoever's 99th on my list. And if you just hit enter again, it will spit back another one. So the next person is number 43. Next person is number 91. And you can just keep hitting enter. The way mine came up to start with, if you have one like this, the N is the number of people you want out. So if we need 3, you could put a 3 there, and it will actually give you all 3 of them at once. On our graphing calculators, I had you do 1, 100. If you wanted 3 back, you could put another comma and a 3, and it would give you all 3 on the same screen, or you just keep hitting enter to get more. Does that make sense to everyone? Okay, so let's just try it. So the 112th Congress of the United States has 435 members in the House of Representatives. Explain how to conduct a simple random sample of 5 members to attend the presidential luncheon, then obtain sample. Now obviously, like, we could all get a different sample here, right? That's kind of the point of being a random sample. So it's not something, there's one on your homework like this. Yeah, you can make up 5 numbers and I'm not going to know the difference. Okay, but the point is for you to learn how to do this on your calculator to get a random sample. So take the 30 seconds to do it so you learn that process, all right? So if I have 435 members and I want to get a sample, how would I do that? We would, assign each person a number. And so first, we need to enter a seed. Let's all do the same seed this time. What seed do you want to use? I didn't hear what you said. I heard 2. I didn't hear what you said. Okay. We'll just go 2. I already read that. Okay, so you go 2, and then what do? Store math over to probability, and you want to store that in your random. So 2, store math, probability, random. So we all had the same starting seed. Okay? Now we actually want to get our numbers. So we go into math, probability, random integer, and what do I need to type in? 1, 435. You can go ahead and put another comma and the 5 if you want to give you all 5 at once. Sometimes that's a little much for your screen. Things will kind of go off to the side. So if you just want to hit enter 5 times, you can do that too. All right, so what did you get for your first number? 214. Did everybody get 214? Yeah, because we all had the same starting seed. So that might be something I would do on a test, is tell you what seed to use so I knew if our numbers matched. What's your second number? Third number. Fourth number. And last number, 160. Something that could potentially happen, you could get repeats. It's random. So I could get 214 again. Could you select the same person twice?
No.
No, so you would just throw that number out and get another one. Okay? Is that all right with everyone? So I'm done. This is the intersections 2 and 3. I posted